assume we have a graph of some sort of curve. Well, if we want to represent that as a vector valued function, then, and by the way, when I say vector valued function, what I mean is that it's a function, it's a standard function, think of like f of x, but what comes out of that function is, instead of being a single number like a scalar, what comes out of the function is a vector. It's a vector valued function. So if we have a graph, think of like a y equals x squared. That's very familiar. We know that that's a parabola. But we may want to represent that as a vector valued function, because we're going to develop some techniques as we go on. And to do that, we need to start constructing things that look like vectors so that we can compute those values. And also, if we want to expand beyond just 2 dimensions, we're going to have to think about things in a more general term. So to do that, what we have to do is we have to parameterize functions. Now, you've probably covered this in a previous course, maybe even 2, where what you do is you take a standard function that you're used to dealing with, and you develop ways to describe them in terms of some intermediate or shared parameter. Like, this is a shared parameter t, so x is a function of t and y is a function of t. Now, this has an added benefit in that it works perfectly fine for functions. In fact, it's very straightforward for functions. But what it also allows you to do is to take a graph of something that you can't describe as a straight function. Remember how functions obey the vertical line test. If you were to drag a vertical line through, you shouldn't strike more than once. But what parametric functions allow you to do is describe the x and y values by some sort of shared parameter. And if you vary the parameter over its space, you get the whole graph without having to worry if one of these variables is a function of the other. So there's a lot of value here in what we're doing. Anyway, so to perform an example, I have y equals x squared. And I'm going to show you 2 parameterizations that we can come up with. The first one is fairly straightforward. If I define x as just t, then I can say y equals t squared because I know that y is x squared. So that's another trick here, is that if you have one already as a function of the other, if you define this, you can plug it into the original relation to get a parametric representation, basically to guarantee one. So let's run through the values here. And this is what you should normally expect. If x is equal to t, then each value is t. But if y is t squared, then we square these values. And so we get these ordered pairs. We get -2, +4. So this is t equals -2, t equals -1, t equals 0, t equals 1, and t equals 2. Alternatively, let's say we parameterize x by -t. So to do that, then we would say x is the opposite of each of these. So that's 2, 1, 0, -1, -2. But when we square that, it doesn't matter. So we still get 4, 1, 0, 1, and 4. So if I start over here at +2, +4, that's when t equals -2, not 0. T equals -1, 0, +1, +2. So what I notice is that I'm actually going down the graph. I'm traversing it in opposite directions. So this one's going left to right, and this one's going right to left. But they still would construct the same graph if you plotted them all over the value space. Now, you can even go further here. Now, I wouldn't recommend this, but you could have come up with something like x equals t cubed over 1 plus t squared. Now, that right there would still be a valid parameterization, and y in this particular case would be t to the sixth, or 1 plus t squared squared. Now, I don't know why you would do that, but it is a valid parameterization that would be able to describe this graph, but it makes things a little more murky. But just be aware that multiple exists and there's not necessarily a right way to do it. As long as you come up with something that works, that's what matters.